here with Michelle from Grobelar, from representing the CTBTO. And we are very delighted to be sharing a session on this important issue. As you know, Michelle has been working with this for a long time, and so have actually most of us. This is about IMS sustainment, and that is, IMS is, as you know, also a cornerstone in the verification system. It's aging, and it's important to keep it up, to keep the credibility of the verification system. But this will be a theme in several sessions over the S&T, and today we are delighted to invite you to quite an interesting series of talk about the technical issues of sustainment. So, you will introduce the first speaker.
Thank you. Yes. Well, firstly, maybe we can, the talks will be for 12 minutes, and then we will have 3 minutes of questions. So we will try to indicate when we have the 12 minutes are up. And then, of course, we have poster sessions as well that are related to the IMS sustainment. There are the lightning talks, which are tomorrow, and then the posters are on Thursday. So please do look out for that as well. That being said, I'd like to introduce the first talk, and it's entitled Recent Developments in Advanced Materials Tailored for Enhancing the Longevity and Sustainability of Hydroacoustic Stations. Please.
Good afternoon, everybody. My name is Mouniati Sherfatin. I'm doctor at the NSTA Algeria. And the presentation is entitled The Recent Development in Advanced Materials Tailored for Enhancing the Longevity and Sustainability for Hydroacoustic Station. So, as you are surely aware of, the hydroacoustic stations of the CTBTO operate under some of the most extreme and challenging conditions on the planet. The stations are located in the deep sea in remote, where they endure high pressure, frigid temperatures, and corrosive salt water. Therefore, sustainment action are crucial, such as regular maintenance, timely repairs, and technological upgrades in order to ensure that these stations continue to function effectively, providing accurate and reliable data. By sustainment these stations, the CTBTO can maintain the integrity of its global monitoring system, ensuring continued compliance with the CTBT and contributing to international security. Of course, the sustainment activities are conducted in relation to the on-land and also to the underwater systems. Here, we address the challenge faced by these hydroacoustic stations, which is corrosion. To our understanding, corrosion remains one of the most challenging conditions by these hydroacoustic stations. The accelerated degradation caused by corrosion poses a severe threat to the structural integrity and operational reliability of the system. Here, the used traditional materials and protective measures are proving insufficient in this hostile environment, making the development and implementation of advanced coating materials very important. These cutting-edge coatings must be engineered to provide exceptional resistance to corrosion, ensuring the long-term durability of the stations. So by addressing this challenge, we can secure the continued functionality and effectiveness of these vital components. So as a solution to these corrosion issues, we propose the technology of superhydrophobic coatings. Superhydrophobic coatings are characterized by their extreme water-repellent properties. They offer promising solutions to the pervasive corrosion issues in this station. These coatings create a surface that minimizes the water contact by causing the water to bead up and to roll off as presented in this image. So it can reduce the likelihood of corrosion inducing moisture accumulation. This water repellent behavior is crucial in marine environments where constant exposure to salt water accelerates the corrosion of submerged structure. In addition to water resistance, superhydrophobic coatings can also reduce the adhesion of marine organisms, such as algae and barnacles. So by preventing both water ingress and biofouling, these coatings can enhance the durability of hydrocaustic stations and extend their life. So let's talk about science behind this. Superhydrophobicity is it's related to what we call the WCA, which is the water contact angle. It is defined as the angle where the liquid vapor interface meets a solid surface. So according to the WCA, this angle, we can define whether the surface is superhydrophobic or not. So for instance, here, as mentioned in the upper picture, if we have a WCA between 150 and 180 degrees, we can say that our surface is superhydrophobic. It is hydrophobic if a WCA is between 90 and 150 degrees. Less than that, it's either hydrophilic or superhydrophilic. And also, superhydrophobicity was mainly discovered in nature. We have here in the lower picture the SEM image of a lotus leaf, where the WCA is 162 degrees. So how is the superhydrophobic surface is fabricated? Surface chemical composition and surface roughness are key factors contributing in the formation of superhydrophobic surfaces. There are many methods and techniques to create roughness, followed by modifications to achieve superhydrophobic surfaces. We have templating, etching methods, hydrothermal synthesis, and most importantly, the nanocomposite spray coating, which offers a cost-effective method to creating superhydrophobic surfaces by using advanced nanomaterials. Here we have the thermal spray coating, which is using high-performance thermosets to deliver robust anti-corrosion performance, even under constant seawater exposure. These coatings form a durable, adherent barrier with excellent thickness control and minimal part distortion, preserving design flexibility. They significantly extend service life, often from 10 to 20 years. It's then reduce maintenance demand and protect critical components like pipelines, structural steels, and offshore platforms. So let's now move to a specific case of study we performed recently. As I stated, this nanocomposite spray coating can be seen as the most adequate and cost-effective technique to achieve superhydrophobic coating. In this case, a new nanocomposite was developed from a high-performance phthionate resin and seal and surface modified titanium nanoparticles. The phthionate resins are considered as one of the most advanced thermosets, featuring an exceptional thermal stability over a wide range of temperature, very low water uptake, a high cross-linking degree, and very low melt viscosity and large processing window, which allow to prepare the nanocomposite through the technique of spray coating. The phthalenyl are synthesized via simple nucleophilic displacement of a nitro substituent activated by cyano functions. Multitude of possibilities are available by changing the phenolic precursor in order to tailor the final properties of the polymer. Nanocomposites were prepared by adding, So prior to nanocomposite preparation, a chemical surface modification is applied to these TIA superhydrophobic nanocomposites. And then the nanocomposites were prepared by adding the necessary amount of the treated nanofillers, ranging from 2 to 6% with an increment of 2% into a glass vessel containing a dissolved phtalenyl resin. So the selected substrate used to assess the corrosion protective properties was carbon steel panel. The deposition of nanocomposites mixture was performed by spray coating process, and the final thickness was about 120 micrometers. Here, we performed an SEM images to study the morphology of our coating. In figure 8, the unfilled resin showed smooth, featureless fracture surface morphology. On the other hand, adding these sealant-treated titanium nanoparticles caused an increase in the surface roughness, and the hackling for all the nanocomposites here showed in the 3 other images, B, C, D figures. So the WCA measurement here is had values over 150 degrees, which is reaching the WCA of a superhydrophobic coating. The corrosion protective properties of these nanocomposites were tested using electromagnetic impedance. And here were the results. The findings showed that adding the titanium nanoparticles enhanced the corrosion protective properties of the coating. A gradual increase in the modulus value has been recorded with the increasing of the amount of nanoparticles. The interesting results are mainly attributed to the superhydrophobicity of this coating. And here we have the evolution of impedance modulus at low frequencies for the sample of a different immersion time.
I'm sorry, we need to ask you to conclude.
Yeah, I will be very quickly. Yeah, very quick. Yeah. As we prolonged the submersion of this of our system into a saline environment, we had like for more than 1 year with the results were very promising. And also, mechanical resistance was investigated, where evaluated the micro hardness, which showed a maximum micro hardness value of 500 megapascal, which is a very good mechanical property. Also, thermal properties were tested, where thermal stability performances using thermogravimetric analysis confirmed that the nanocomposite coating retained the structural integrity over a wide range of temperatures starting from 50 until 500 degrees Celsius. So as a conclusion, our superhydrophobic coatings create a barrier that significantly reduces water contact. And in order to prevent corrosion in these harsh marine environments where we have our hydroacoustic components, phthalate titanium composites can be a cost-effective candidate for the use with a multi-layered defense strategy against corrosion. Also, the reduced corrosion and maintenance needs translate into long-term cost savings. The confidentiality verify the long-term applicability of the superhydrophobic coating in hydroacoustic station, further studied under real marine conditions and necessary, ensuring the solution meet operational demands. So for further actions, we'll focus for the feasibility and scalable manufacturing of this development superhydrophobic coating, and also to conduct real sea trial to assess the performance of these superhydrophobic coatings when applied to various components as well as the CTBTO hydroacoustic stations. And thank you.
Thank you so much for giving us insight into this very special component. It will take us time for a quick question. If there is one? Yeah.
Actually, two very quick questions. The first one...
Could you state your name, please?
Oh, sorry. Mario Zampolli from CTBTO, from IMS, Hydroacoustic team. The first one is, can these coatings be applied also to plastic substances, rubber-like and things like that? And the second one is, do you have experiments on the effect of these coatings on flow past objects in terms of vortex shedding and things like that?
Yeah, the experiments first were tested on a steel panel. And for rubber, it was at this time it wasn't done. Surely it will be done. Yeah. And second one, we conducted here. Back. I can't do it back. Okay. We conducted a mechanical resistant investigation, but for the flow, we will consider it. Thank you so much for your.
Thank you so much.
Thank you.
The next on the list is entitled Integration of Mass Position Monitoring and Auto-Centering on Indonesian Seismic Networks.
Good afternoon, everyone. Let me introduce myself. My name is Amir. I work for the Agency for Meteorology, Climatology, and Geophysics of Indonesia. And at this time, I would like to talk about the integration of mass position monitoring and centering on Indonesian seismic stations. So this is the outline I will talk about. The first would be the challenge in Indonesian seismic network maintenance, the system integration as an alternative solution, and lastly, the proposed advantage and challenges of the system. Okay, the first one, the challenge in Indonesian seismic network maintenance. It covers the first challenge, the fragmentations. We do have about 5 or 6 instruments from different manufacturers, and they share nothing in common. So they all have their own application and their standards. Those differences create an inconsistent monitoring, such as one brand, they do scale the mass position by their voltage. So -4 to 4 voltage, while the other put a scale on 1 to 10. So that's one of the differences. The second challenge is the geographic scales. Indonesia operates about 552 stations throughout the Indonesian islands. So it's a lot of stations to monitor by a single person or just one organization without a unified dashboard or interface. Now those add up to one of the core issues is the compromised sensor mass position, how we would be troubled with this phenomena when we are not be able to monitor mass position regularly and their overall health regularly. So the proposed solution is a system integration as an alternative solution to give those sensors from different manufacturers a unified and scalable web interface to monitor and take actions. We propose a web-based dashboard because most of the manufacturers, besides their own applications, they also provide a web interface or graphical user interface. And we use HTTP to post and get data from those digitizers. The unified dashboard is a web-based platform that brings together data. Mainly, as of right now, it's the mass position. And we could see their name, the digitizer name, their station, their mass centering counts, and the state of health. We simplify with colors to make monitoring easier. The second part of the system is the controller. The integrated controller consists of one, the check digitizer. It eliminates one step in monitoring. Prior to this system, the monitoring consists of us taking the visuals from every sensors, 500 of them, and we check manually by clicking their respective IP addresses. This web is tackling those problems by listing them in a one page, so we just click them and could check them. It also have the center mass option. It will be a HTTPS post, so the web posts to the digitizer to center the mass should it be needed. And lastly, it also have the auto center, and this will be the core of this web to unify all digitizers, how to auto center them not through the web interface, but not through the digitizer, each one of them, but through a web interface, significantly saving valuable time and resources. So lastly, the proposed advantage and challenge. These web interfaces would be proposing enhanced operational efficiency, implementing centralization and automation streamline process. The second will be the focus on the data. A corrupted mass position would be critical for the seismic data. It would cause clipping. Now, when the earthquake or the surge in earth movement gets so big, and the mesh is not on the center, it would clip, and it's not good data. The third thing is minimize downtime. A corrupted sensors is unusable. We use 3 components, the vertical, horizontal, and 2 horizontals. But when the mesh is corrupted, especially the vertical component, it's unusable. So by monitoring the mesh, we could see how's their behavior. Typically, when sensor is nearing the failure, they would center the mesh frequently every day. Could be 10 times, 100 times, or whatsoever. They are failing their own mass position management. And with this web integration, we could monitor their centering counts and possibly turning them off or tell the staff to look after them before they get failed. The last advantage would be scalable blueprint, because HTTPS and web interface is giving us an opportunity to scale our monitoring system. Unlike the manufacturer's interface, you could not put them together because obviously there are different brands and not possibly could be put into one together. So the web is offering those advantages. Now, lastly, we also have challenges because the backbone of this web-based interface is HTTP. Most of our digitizer does not support HTTPS with their encryption, so we should have a better protocol, or maybe we could use VPN or something to encrypt the data to prevent infiltration and other cyber threats. Okay, that's it from me. Thank you for your attention.
Thank you for giving us the insight into your huge network. Are there any questions?
Thank you. As you said, you have 552 seismic stations all around Indonesia. You are proposing this integration among those 552, or these 552 includes that CTBTO also?
That would be including the CTBTO.
So, as you said, these are different protocols they are using, different parameters they are using, or the numbers they are using. Do you have to rewrite everything to integrate all these different stations or different networks parameters into one? You have to rewrite everything, or just on this web-based, the model you are proposing?
Okay, thank you for the question. We look back at the digitizers, their scale, actually. If we're talking about mass, that would be the how their mass is further, the distance between 0 and their mass position. So every digitizers and sensors have their own scale. But generally, the scale is the same. It's measuring voltage. Most of them are ±4 voltage, so we could transfer them into my proposed web base would be the scale from 1 to 10, -10 to +10. So if one of them using -4 and 2 +4, it just be calculated from to -10 to +10. That would be in general.
Thank you. No more questions? Thank you so much. Very interesting.
Thank you.
Thank you. So the next on the list is, the title is Full Chain In Situ Calibration of Hydroacoustic Hydrophone Stations. Please.
So, dear chairs, dear participants, thank you and good afternoon. My name is Ch2. I'm the head of hydroacoustic team in engineering and development section at CTBTO. So that work was conducted together with my colleagues from our team, Mario Zampoli and Dirk Metz. Thanks for their support, and also thanks for my management for their support. So the content of this presentation, actually, I will talk briefly about the full chain calibration, in-situ calibration methodology for hydroacoustic hydrophone station. So that actually is a feasibility the feasibility of this initiative is currently being studied. So there is no commitment to that methodology. So internally we are working on that technically to make that happen for our hydrophone station. So this is a general picture that we already know. So in this slide you see the map of IMS network, and each pin represents the IMS station. So in total 337 stations are facilitating, and 90% around of these stations are built, and they are sending data to Vienna. And in total, there are 11 hydroacoustic stations, and these are detecting the pressure variation in water, and then capture signals transmitted across the long distances in ocean. That is something I think most of the people in here familiar about. So it's hydroacoustic network has 6 hydrophone stations. They are made up of bottom moor triplet deployed at SOFAR channel, and they are sensitive to acoustic pressure variations in oceans. And beside these hydrophone stations, we have also 5 T-phase stations. They are land-based seismometers, which are more sensitive to ground vibration and detects hydroacoustic waves transmitted through the earth crush. And on the right side, you see the image, the schematics of a hydrophone station. So from the shore to the offshore, we have the shore facility that keeps the electronics. And from there, we have the trunk cable that connects the shore facility to the hydrophones. And we have 3 hydrophones, as you know. And at the first hydrophone, we have the electronics that converts the analog signal into digital. So at the moment, I will explain it in more detail, but at the moment, the only capability that the hydrophone stations are just the calibration of the electronics. So the hydrophone, the analog part of the station are not considered at the moment. So that is something, therefore, we would like to want to have an in-situ calibration to consider those effects as well. So in this slide, you see the details of calibration effort before and after deployment. So prior to the deployment, so an extensive and inclusive full chain system level calibration at operational depth and temperature in the laboratory environment are done. The hydrophone and the preamplifiers are tested in low frequency test facilities, while the digitizers are tested in a laboratory environment using simulated inputs. But once the system deployed, so once it goes underwater, the underwater segment digitizer electronics calibration is performed from the CRF. So that means that the contribution of the analog part do not consider in the calibration. And this analog part contains the hydrophone, the riser cable, and the preamplifier, which is very critical from our perspective. And this is how the calibration is done after the deployment. So from the CRF, a signal is sent to the electronic bottle, and it's a different type of signals, a continuous signal that we triggered from the CRF, and the electronic response is captured and compared with the nominal response of the system that was initially calibrated during the fabric acceptance test. So you see in here, the hydrophone and the preamplifier are not considered in this chain. So why the full chain in-situ calibration is important? So the hydrophone is actually the primary sensing element, and its acoustic performance is critical. And hydrophone performance may be affected by the external influences. And the analog part of the system may degrade over time, and the potential degradation is currently not accounted for in the system's traceability. This is a significant concern as CTBTO aims to keep the station operational well beyond their original design life until it fails. So therefore, we have to have knowledge about the analog part of the station as well. Full chain in-situ calibration would also allow us the assessment of the station health more accurately, thereby supporting sustainability planning and ensuring long-term reliability. And also it would serve as a key measure to ensure performance, consistency, and maintain the continued effectiveness of the hydroacoustic network. So I just would like to briefly give some examples from the not recent, but past studies. So in early 1990s and 2000s, there are a couple of experiments to check the full chain acoustic response of the some stations. So that happened in 1999 on the left at Ascension Island, and seismic air guns were deployed to produce acoustic pulses. And these pulses were recorded by a calibrated hydrophone and compared with the station's hydrophone. So this method was promising, but the implementation is not so easy because the direct acoustic arrivals were contaminated by the strong seabed reflections, as the hydrophones in this case were positioned close to the ocean floor and the air guns were just below the seawater. Another study was carried on 2000. Instead of air guns, imploding spheres, glass spheres were investigated as an alternative to air guns. And the problem in the issue in this exercise was the spheres has a frequency response from 200 Hertz up to 800 Hertz, which is not the frequency bands of the PTS. So I'm not going to go into that detail, but there's a couple of calibration standards available. So IEC 60565 is one of them, and it describes the methodologies for the calibration in laboratories. But that standards defined primary and secondary calibration methods across a wide frequency range, and that standards can be used as a baseline for in-situ calibration, and the in-situ calibration can be built according to this understanding. So these are the documents that we considered at the moment during our assessment. And from those standards, I just would like to give some highlights about the methodology. So there are two types of calibration. that can be done on the field. So first one can be a hydrophone calibration using a calibrated projector. So in here, the projector emits a sound into the water, and by knowing the physical properties, I mean the calibration chart of the projector, you can calculate the sensitivity of the hydrophone. But in here, you have to know the distance in between the projector and the hydrophone very accurately, because this, in the formula on the right side, you see D is the distance, and due to the ocean conditions, the change in the distance may affect the result. And the challenge in here is that the frequency range of the PTS is very low, and this is something that we will discuss tomorrow in the meteorology session. But the calibration of the projector at those frequencies are very challenging, and there are actually a couple of NMIs, National Meteorology Institutes, can do this, and this is something needs to be spread out around the world. The second method is, instead of using a calibrated projector, a calibrated hydrophone can be used instead. And in here, you have to have, again, a projector that emits the sound, but by knowing the sensitivity of the hydrophone, you can compare the reference hydrophone with the hydrophone that you want to calibrate. In here,
Can we ask you to...
Yeah. Okay. So the most challenging part in here that you have to have two platforms, so that increase the financial burdens. So before I jump into the conclusion, so the key challenges are the calibration of the equipment, availability and meteorological traceability of the projectors and hydrophones are limited. So due to the low frequency, the number of oscillations at the hydrophone side without any overlap due to the reflections requires the use of signal processing techniques to reconstruct the signal sufficiently long to determine the signal's amplitude and phase. So this is especially challenging below 20 hertz, I can say. Deep water is one of the big challenges because you have to deploy your equipment up to 1,400 meters to reach the SOFAR channel. At the moment, there are no standard calibration procedures for Ch2 that consider the deep ocean environments. So accurate knowledge of the coordinates of the hydrophone is essential if you want to use the second methodology, comparing with a reference. Open ocean ambient and propagation conditions needs to be well defined, and the remote location gives lots of challenges and costs. So what is the future action in here? So we would like to work on the feasibility and the preparation. So we are very open to cooperate and make a joint work together with the institutions who has offshore marine engineers, and we would like to contribute, we would like to ask their contribution for the calibration effort and provide logistical support at remote stations. And we also get their support for addressing station-specific permitting issue. Exploring of the equipment is something that we need to work on, and we need to also work on the establishment of calibration methodologies and procedures. So once we finalize this feasibility, we would like to do a sea test, much closer than the stations, to check the procedure and the equipment. And after we have a confirmation from all these methods, softwares and equipment, we will do the calibration work in one of the hydroacoustic stations. HO1 would be the one of the candidates because it's more accessible from land. So by saying that, I would like to thank you for listening, and if you would like to have some discussion on that, I will be here tomorrow and also during the rest of the SNT. So thanks.
Thank you. This is one of the more important issues at hand in the IMS sustainment, since the hydroacoustic is so very expensive.
Yeah.
So thanks for giving us this insight. Is there a quick question from anyone? Yep. Could you state your name, please?
Josephat Mullo from Kenya. Thank you very much for that insightful presentation. And if I got it right, the reason why you are now going to full chain in situ calibration is to get the condition of other equipment like the riser cable. So how will the full chain in situ calibration now give you information about the riser cable? Thank you.
Yeah, thank you for the question. Yes, that's correct. I mean, now only the electronics can be calibrated from the CRF, from the shore side. But with the in-situ calibration, we can have an opportunity to check the chain from the hydrophone until up to the electronics on the shore side. So that's the main profit of this exercise.
Thank you. Then we will refer the rest to the break after. Thank you so much.
Thank you.
Thank you. So the last talk is, the title is Erosion and Subsidence Prevention at AS007, which is in, the other code is BRDH, Auxiliary Seismic Station for Sustainable Operation and Maintenance. Thank you.
Thank you. Good evening, everybody. Yes, it's become good evening, and as the last talk, I do not want everybody to be sleepy. So unlike the previous all research-based lectures, I'd like to show you a photo album actually to show the European Union contribution to BRDH. What we faced some problems. Me, Mohammad Rajib, working as the PKI operator and principal user of the NDCBD, along with two of my senior colleagues, Dr. Ghulam Rasul and Hasin Rahman. So we have the Bariyadhala station, auxiliary seismic station, which is about 200 kilometers from the capital city, Dhaka. And this is located in a tiny country comparing to this world. We have only one this auxiliary seismic station who faced a little bit of problem previously. This is the location of the station. It's about on a top of a hill, about 70 feet above the mean sea level. Not so very tough condition to go there, but still this is an unmanned station. This is located in a reserve forest, and the area is not so much populated yet. So we have quite a bit of history of the European Union contribution and the CTBTO technical cooperation, starting from 2004. The station actually started operation in 2011 after all this feasibility study and the site selection, everything. During 2017, the upgradation of the installation of advanced GCS system that happened. In last 2-3 years, we had some technical setup changes in the computer setup, and in this year, we had a major repair maintenance activity had to be done for this erosion and subsidence prevention. As I said previously, we had one problem, major problem at the vault. As I said, it is above this 70 feet hilltop. Still, there were some flooding occurred during the rainy season. So, as you can see in the vault, there were some water infiltrated through the geological formation surrounding it. So, what we had to do some kind of RCC work. with the epoxy cement and waterproofing admixture. And after that, this problem was solved. But what we have found in couple of years, actually, not in 2-3 years back, some erosion of the hill of the station surroundings that started to occur, and also the inside the building there were some subsidence we observed. This happened. First, it was observed in 2021. We regularly visit the station, so we found the lowering of floor cracks during that time, and especially at the northwestern corner. This is about 7 to 8 feet from the seismometer seismic vault. In 2 years' time, actually, it became more than 2 centimeter in width. So it was very quickly subsiding in our observation. Also, the vault platforms, though we reinforced the vault by doing some work in 2017-18, the vault was okay, but the surrounding areas were subsiding. As you can see, the fracture width, it became nearly 2 centimeter. On the east side, it was 1 centimeter. So on one side, it was subsiding. The other side, it was a little bit less subsiding. At the outside of the building, there were also cracks. In August 24, we found that the cracks just adjacent to the vault, it was observed. And it was very tiny one, 0.5 to 1 millimeter, was first seen at that time. At the outside of the building, it was also, we found that one. So we concluded that the whole building is at risk. So this needs serious intervention. And we started discussing with the CTBTO, and they have started responding immediately. We found near the hill area where all the construction work ends, more than 3 centimeter cracks were formed. So we were assuming that that part, I do not have the, on that picture, on the right-hand side from my side, that part is almost hanging due to the erosion of the subsiding soil. So it was necessary to have the serious intervention. On the surrounding hills also, we have found that there were some less amount of those trees are there, so the soils are easily draining out during the rainy season. So we started discussing, as I said, first in May 2023, it was discussed during an unofficial visit to the VIC. A problem report was opened, and then after several discussions through mail, a request letter for quotation was published by the CTBTO, and we provided a work order to one subcontract from the Bangladesh Atomic Energy Commission, the technical counterpart of the CTBTO in Bangladesh. The repair work started during last week of January 2025, and by the end of first week, we completed it and started the network again. These are just some of the activities. As I said, I will show you just photo album. There is nothing research, but we had some good work at this station. So we had to dismantle the existing structure, the floor of the station, entire station, as per requirement, such as the RCC work, floor tiles, brick work, cement plaster, everything we had to dismantle it. And later, the outer part also. As we said, the outer part also was showing some kind of crack, which was increasing day by day. So we had to repair that one as well. This is a little bit outer area. The engineer said that we will have to make the drainage channel to run the rainwater very quickly and not touching the station building. So the drainage channel was planned and it was designed. This is some of the safety canopy. All these pictures, as I said, this is just to acknowledge the European Union contribution. So what were included in the work order, we had to conduct every item of those activities, and after every work we had to send all those photos to the CTBTO. They were monitoring remotely, and we were taking those photos of every work. I could say each day we had a photo when they were working. So earthwork in excavation was done surrounding the building. At that time, the complete setup of the inside the network, the connection to the satellite, everything was disconnected. So we had a nearly 4 or 5 months stop of the BRDH connection to the IDC. Later, we had to do some retaining wall, floor, slab, rainwater discharge channel, everything we did successfully. These are some of the works. The pictures, we did it inside the building, outside the building, surrounding the building to make all those happen. And later, it became actually a new look. The floor tiles was given new, the entire electrical work was done. The floor tiles or the pavement tiles outside the station building surrounding the solar panel, everything was done new. There are some brickwork, paint work, cement work was also done to strengthen, to make the station a newer look. These are some of the inside activities, like electrical activities, the cleaning of the existing windows. According to this as-built drawing, we were provided by the engineers. So, as I said, the erosion was occurring surrounding the hills, so we had to do some preventive measures there as well. There were some boundaries with the barbed wire fencing surrounding the hill. So we had to construct some new fencing. They repaired and painted the old ones as well. And partly this was funded by the Bangladesh Atomic Energy Commission because it was inside the work order. Some part will be contributed by the European Union, and some part will be done from the own budget of the BAC. This was the plantation in cooperation with the Department of Forest we did, and the result were quite immediate. We found some improvement in the calibration values immediately after the repair work was done. We did the calibration, and the erosion was also reducing, but it will take time because just we finished only a month or 2 months ago. So this is the new look of the station building. What I can say that we are the international monitoring system. Internal monitoring system, it should be a verification today, tomorrow together with the CTBTO people. I'd like to actually acknowledge here 2 persons from the CTBTO especially. Ms. Irene Biachi, who is most probably online. So thank you, Irene. It was your idea to start the discussion and to, I should say, save the building. And then Ms. Chulalak Sandud, who is now in charge of the seismic engineer, who is now in charge of this station. So both of them actually were completely online with our team to make this happen and make this successful. Thank you very much, everybody.
Thank you. It's very nice that you give credit to the CTBTO and the Today, Tomorrow Together. That was really nice to hear.
Thank you.
Is there any questions on this? No? That's probably because it's the last on the day.
Thank you very much.
It sounds like a very serious technical challenge that you have been able to solve, so all credit to you for that. So thank you
very
so much.
Yeah.
Thank you for attending this session. We have a lightning talk on the same subject tomorrow at noon in the Winter Garden. So we look forward to see you there again. This is a topic that will be on the agenda for the CTBT for a long time to come, I suppose. Good, thank you.
And thank you very much.